There we go. The recording. Looks like it's recording. Okay, thanks. Okay, so electric fields. So let's do summarize summarize some of the stuff we learned last time. So summary is that, okay, so what we learned is that basically we have, as you guys well know, we have these atoms that are made out of protons and neutrons at the center, and then they have, in ways that we won't get into, not in a circular pattern outside the nucleus, but in some way outside the nucleus, they have electrons outside. So everybody knows that. So from that comes this concept of, and so everything is made out of these, right? Well, I mean, there's other particles that I don't really, I'm into, but let's just, for the sake of this class, talk about protons, neutrons, and electrons. And then, some of these things too. So some of these entities have a charge, have something called charge. The reason I keep talking about something called charge, because at least I have like preconceptions about what charge means, which sometimes are true and sometimes isn't, or what a charge does, I should say. Sometimes there's no. So just for the sake of like, just kind of play along that we're talking about, this is like some new quality of some, let's call it a quality of a quality called charge. Okay, so we call that Q. This quality for a neutron is 0. For a proton, it's, for, we don't know why, it's positive charge. It could have easily been the other way. And then but both the electron and the proton have equal and opposite charge. And I'm sure we can talk about for a very, very long time about the mysteries of the universe, that only electrons have precisely this 1.6 times 10 to the minus 19 charge, like every single electron in the universe has that. And then another mysterious thing is that every proton has the same positive charge, which mysteriously happens to be exactly equal to the positive amount of charge that every electron has. So very, very strange. And then, but, interesting as it may be for this class, and there's all these other questions that everybody's, or at least some of you are wondering about, maybe not at 8 o'clock in the morning, maybe you'll start thinking about this some weekend in the semester, about why the electrons being negatively charged don't collapse into the nucleus, or why the protons, these positive charges here, aren't pushing each other away from the nucleus. But we're not going to get into that in this class. Just there's some explanations out there for these things. Anybody curious about that kind of stuff, by the way? Anybody have answers? No, I just, as I'm saying, we're not going to discuss it, I'm like opening
There's
up.
a law that describes it, correct? I'm just forgetting the name.
Yeah, so there's, well, okay, like I guess I was sort of like fishing that somebody would ask something just so I would say something, so we would leave it alone, because it is kind of stuff that bothers me. But so the reason why the protons, they can kind of sit next to each other, is because of, we talked about these different kind of forces. There's a force of gravity caused by masses, and although it's a very weak force. It's, we said, like, I think it was 10 to the 40th smaller than the electric force. But because you only have positive gravity, because of that, it tends to kind of dominate our universe from the way we feel. Like, we feel strongly pulled towards the Earth. The Earth is strongly pulled towards the sun. I guess, we're being pushed and pulled by, galaxies or whatever. I'm not an astronomer, but so I keep forgetting what's going on. But so that's the force of gravity. Then we have the force of electricity, which is much stronger. And let me actually write down this thing about, so this is 3. So that, but it's much stronger, but then not everything, like atoms are mostly neutral. They have equal number of protons and electrons. So if everything in the universe was charged, we wouldn't even feel gravity, because the forces of electricity are so much stronger. And they're both a 1/r² phenomenon. So for example, anything, as we know, anything that's got charges on it is applying a force to another charged thing by this formula, which is Coulomb's law. I'm just gonna, okay, it is 1/r². The thing is it has this 1/r² power, means that it's a very, very strong force close up, but drops rapidly to the farther out. Now there's another thing. So this is, I'm just saying this for your amusement. It's not part of the sort of what we're going to be discussing in the class. So why don't protons in nucleus push each other away? And that's because of something called, this is like, I didn't name this, the strong nuclear force, or the strong force, which is, it's not an electric force, it's yet another force that basically keeps the protons together. So it's pulling the protons together. But if I remember correctly, it's sort of an e to the like the force is some kind of a e to the minus 1/r² kind of effect. I know it has this exponential minus exponential effect. So just as the electric force falls off rapidly with this 1/r², so it drops off very quickly, right? This is what this 1/r² tells you. As you move further from a charge, the force drops very, very quickly, right? But the strong force, which is only sort of useful in the nucleus of the atom, drops even faster. It drops off really quickly. So the distances where it's effective are, I don't know what the numbers are, say 1 times 10 to the minus 11, 1 times 10 to the minus 12 meters kind of thing. And this is a force that's keeping the nucleus together, okay? And this is part of the reason why we can't get an explanation of why we can't get atoms with atomic numbers bigger than a certain amount. Like that means that you can only have so many protons in a stable way in a nucleus, is because even over those short distance of a nucleus, the nucleus gets big enough so that this force, because of this really rapid drop off, fails even inside the nucleus, which is a really, really small distance. And so if you pile enough of these protons next to each other, the distances, again, you're talking about, I'm probably really underestimating this distance. It's just this strong force falls off very rapidly. So basically you can't get an atom with a bigger number of protons than a certain amount. And then the electrons, that's getting into a more detailed explanation. quantum physics discussions and nuclear shells and stuff, but there are, if you do the math, which I haven't done in a long time, we were just working on in grad school, so I'd have to go look back doing it, but I remember the result is that there are certain sort of stable or high probability places for the electrons to end up around the nucleus, and none of those are close to the nucleus. So they end up in these high probability places outside the nucleus, but they're not in a circular, they're not like orbiting, obviously, the nucleus like a solar system, but they're in sort of, you can think of them as being in shells, like, or probable locations around and outside the nucleus. So anyway, just sorry about that digression, but I think it always haunts me or worries me why the nucleus isn't falling apart and why the electrons aren't falling into the nucleus. But those are the best explanations I have heard. So okay, so we have these atoms, and this is the basic unit of charge. The upshot is that we haven't seen anything that has a charge that's different than a integer multiple of this, either positive or negative. So every charge, every realistic charge every real charge in the world is made out of a multiple of 1.6 times 10 to the minus 19, positive or negative. Okay. And again, if you got two particles that have this quality called charge, then this is the force between them. Okay, and the force is, you have to also remember that this is, and I apologize because I tolerate this in myself, but I won't in your tests, is that remember that this is a vector. So, this is just the amplitude of the force, what I just drew there, but you have to actually remember that this is a vector, and you have to remember that because we're talking about two charges in this particular case, they are either they're working on each other. They're either attracting each other or repelling each other. So you also have to remember when you write a force down is who is working on what. So for example, the notation here is that this is the force on 2 by 1, okay, with our notation. And then you put a direction for this vector. And, I'm just going to call it E sub r, which is a unit vector pointing from 1 to 2. Just I'm going to define it like that right now. And what else do I want to say? So this is called Coulomb's law. This is kind of Coulomb's law, this equation. Okay, does anybody have stuff that confused me or continues to confuse me? As always, like this unit vector ideas, the vector thing. Does everybody's good?
Sir, I just have a quick question.
Sure.
Why is the arrow pointing to Q2, not to Q1?
In
Or
this
that's not the
case,
case here?
no, I guess in this case, so like if this was assuming that this is a positive charge and this is a positive charge. So there's a force pushing Q2 away from Q1. So that's why I had the arrow pointing. So if Q2 was a negative charge, I guess the arrow would point in the direction of Q1. Is that what you're asking?
Yeah, basically.
Yeah.
So back also to where you said F21.
Mm-hmm.
So you said Q2 by 1. Can you say that
Yeah,
one more time, please?
Sure. Let me say it one more time. So, okay. Let's see, how can I say this? Okay, so let me take a couple of steps back. So Q1 is positive. Let's assume Q2 is positive. So what we're trying to say is that, oops, there is a force on Q2 caused by Q1 that's going to push Q2 away from Q1 in a certain direction. So a force caused on Q2 by Q1 that's going to, and that force has, assuming these guys are separated from each other by R, the amplitude of that force on Q2 is this quantity. And the direction of that force, because we're assuming they're the same positive charges, is away from Q2 in this direction. So this is E sub R. So this is a unit vector, so it's not messing up. It's only giving me direction and no amplitude. The reason for that is then I can play with the amplitude part of this equation separately than the direction part of it. Okay. So I don't know, I'm trying to think of an analogy. So because this has confused me, guys. Lloyd didn't ask this question, but I kind of think of the amplitude as your foot on the gas and this direction as like the steering wheel. Okay, so the reason you separate it out is because then you can increase the force or decrease it, or think about what would happen is if you increase or decrease the force. And like by putting your foot on the accelerator or taking it off, and then you can separately think about what would happen if there's changes in direction on this force. But Lloyd, does it, the first half of that, did that answer your
Yeah.
question?
Yeah, thank you. It's because I remember from high school, I was struggling a little bit with this.
Okay. And then it basically, all the information's there in this equation about what would happen if Q2 is negative, say. That way you'll have, positive Q1 times minus Q2. So the sign of this force ends up being negative. Okay, Q1, Q2 ends up being negative if one of these guys is a negative charge. So assuming this guy was negative or vice versa. And so what that means is the amplitude's the same, and you can think of this being a negative e to the r. That means you're, driving in the other opposite direction, but with the same force. Okay. So again, this is a unit vector. So the amplitude is just there's nothing magical about it. It's like just what do you call it? Our definition of how we're trying to separate out a direction from the amplitude, so it's easier to deal with in a mathematical way in an equation. So the amplitude, if you look at the amplitude of these unit vectors, they're always one, so they don't affect our amplitude calculations. And I'm just kind of like, there's, E sub R is basically a direction away from Q1 that Q2 has. It's not a set definition. I'm just calling, if this was a direction away from here, this would be E sub R. I might just as easily, if I'd drawn it like this, E sub R would be pointing in that direction. I'm just sort of like, just saying it's a direction vector with unit amplitude. That's the critical thing in it. So, and again, that's just for mathematical convenience. But anyway, it always confused me. So I thought maybe I just confused you guys more. What else do I want to say about this? So the other thing that I beat on over and over again in the first lecture was that the way or either the definition of a force or the way you know there's a force on something is that it has an acceleration. So what do we mean when we say there's a force on Q2 at Q1? It means that there's something that's making Q2 accelerate in this direction. So we're saying it's the direction of the force is this way. Okay, and it's a force. And if you have a force, this charge, this entity has a mass, so it has an acceleration. So in real life, that's how you would in fact measure or realize that there is a force on something, is when you see it accelerate. And that's pretty much kind of the only way you can tell if there's a force. You know, you have, so anyway, that's the Coulomb's law. Okay, so now let's get to the fourth item to remember, which is, this is not part of Coulomb's law, but something that's very useful. And we said it's only an approximation, but for everything that electrical engineers would deal with, it's like true. It's called the superposition principle. It's a PAL or PAL, yeah, principle. Okay, which says that if you had multiple charges and you wanted to see the effects, what's gonna, like, if you wanted to calculate the force on Q3 caused by Q1 and Q2, you could separately figure out the force caused by Q1 on Q3, and then separate the force Q2 caused on Q3. So that would be F 32. And then you would sum those up and get the total force. Okay, so force, I don't know how to even write that. So the total, let's call it total force on Q3 would be force F32 plus, this is vector summation. Okay, so you vector sum of these things, and that's called superposition. And that's very convenient because we can figure out that when we have a whole mess of charges acting on a charge, we can look at the forces individually and sum them up, or as we saw, more likely do an integral, which is kind of a continuous sum. Okay, but this is what allows us to do that, the superposition principle. Okay, so that was Coulomb's law, and then we also talked about electric fields. And I made the claim that an electric field is really just a conceptual idea, and it's sort of all it's doing is it's taking this equation which is Coulomb's law, and it's separating, it's bringing this Q2. So I'm gonna let me just not change the charges, just keep it like that, or just erase it. Let's erase that. That. And then I'm gonna move this guy over to the outside. I'm not changing anything. Okay, guys, I'm just moving stuff around. And then I'm going to put a bracket around this part of the force. So again, not change the equation, same equation as we had before for Coulomb's law. It's just that I'm going to call this the electric field, I guess, the ER, okay, times Q2. Okay, so the force would take this multiply by. I'm just rewriting the way the equation looks, and I'm calling this electric field, this part. And the idea is that this is convenient because then I can imagine, again, I can imagine that this charge Q1 is creating this thing called an electric field all around the world, all around the universe. And then I can think of the effects that this electric field has on a charged entity anywhere there. And the idea is this is called, a test charge. A lot of these are conceptual concepts, guys. I think this is another thing. I'm trying to think of what confused me when I was studying this thing. Is there's like one real effect, okay, so far in electrostatic, and that one real effect is that if you have charge, another charged particle can get you to accelerate in some direction, or another set of charged particles can get you to accelerate in a certain direction. That's kind of the only thing that's real so far. Everything else, we're kind of like slicing and dicing equations and vectors and stuff. It's not clear why we're doing this maybe, but it's basically so that when we start solving problems, or conceptualizing problems, it's convenient. Okay, so like this electric field concept, it seems, strictly speaking, it's kind of unnecessary, right? Because I didn't do anything different. I didn't give you guys a new law. This is the same law, Coulomb's law. It has the same information in it as what we had defined before, but for some reason I decided to burden you guys with this new concept of E field. Why am I doing that? Is because it's, as hopefully you'll see, it's convenient to have this concept of electric field being associated with a charge that's causing it. And then we can think about, then we can do if-then analysis about what would other charges do as they're interacting with this electric field. So again, the upshot is nothing new in this electric field. We just took all the stuff, the charge that's creating the electric field, and all the information about the vector, everything other than the charge that the force is acting on, we took that out and kept it, but we took that out, we called everything else electric field. What else do I want to say? Okay, so then we talked about the electric field, calculating it. Okay, so this is the first, this is a good lead to electric field. So let's talk about electric fields a little bit more. So if we were just mathematical people, okay, which I'm not, you could just stop here, right? You could just say, okay, well, have a charge somewhere. I have, I'm going to think about the electric field all around it. I have the equation to calculate it. Okay. But, sometimes for most of the rest of us, it's helpful to have a visual. Okay. So for example, like a good example I heard is that, let's think about topography, right? You could have, theoretically, you could have an equation for the height of the surface any point in the US, right? You could theoretically have that equation that says, hey, if you're sitting in wherever, if I'm sitting in I'm in Del Mar in San Diego right now, I'm at a certain height, an equation would define that. So that's possible. And that's kind of like this. But to help visualize, people have made topographic maps, right? So I'm sure if you guys have gone hiking or whatever, you've seen this. So let's say, if you have this would be like a mountaintop or a hilltop. And then maybe you have like something that's like equidistant, and you have another height out here. So basically you have a topographic map, geographical map. Okay, instead of just having an equation. Huh. A participant with live transcription be enabled for enable. Interesting. Cool. Okay. Um, so this is, concept of a topographic map. So you have kind of a similar thing for an E field. Okay. So these are, this is the concept of electric field lines that I'm sure all of you guys have seen. Okay. Any question about where I'm going with this? About, saying we're basically creating a visual for the electric field, again, that I think most of you have seen. And so this is the way to think about it. Let's say you have a positive charge sitting at the center, and we kind of anticipate that when you have a positive charge somewhere, so think of it if you were a test charge. This is the way I think about electric field. So I could put a test charge here, another positive test charge here. What would happen to it? It would get repelled, right, in that direction. If I put a positive test charge here, it would get repelled in that direction. If I put a positive charge here, it would get repelled by some stronger force in that direction, and so on, right? So basically, the electric fields are radially coming out of this charge. Okay, so if I was gonna, let's just draw them at 8 points. So, let's say we just have, think about, so let's just draw what this visual looks like in these 8 points. And so what is this visual? It says, if I put a test charge here, it's going to get pushed in a certain direction. So I have a certain electric field there. So the way the visual works is you draw an arrow here, okay? And the direction is the direction of the force or the electric field. And the length of the arrow, okay, tells you the strength of the electric field, okay? So you'd have these vectors at these 8 points. And these are just these are just 8 points I picked. I could just go continuously draw more points. And since the test charge, we're talking about the test charge being here and this being radially. So if all these guys are the same distance from this charge, their amplitude is going to be the same, and they're all going to be pushing out away from that guy. Okay. So by analogy, then if I go out a little bit further out here and think about that one or that guy or that guy, then again, the force is going to be pushing that guy away, that test charge away. But because it's further, the distance is further, the force would have dropped by 1/r². So the arrow ends up being shorter. So this is just a visual depiction of what this electric field looks like around this charge. And it's not saying anything other than what this equation is saying. Is just a visual aid. So that way you can kind of like immediately look at this. If somebody had drawn you this, you can immediately go, okay, this electric field is radial, is pushing stuff away, and it's dropping off at distance away. Okay, and that way you can have these drawings that you've probably seen in books and stuff for weird, shapes that people have worked this out. Instead of giving you equations, you have a visual of what the electric field line looks like. Now, one of the things that you should be careful about is this arrow doesn't mean that this in our definition, in our visual description, this arrow doesn't mean that we're describing something that's working over this length. This arrow is giving you the amplitude and the direction of the electric field at this point. So we're talking about this point only, but because we had to show the amplitude visually, show the amplitude, we drew a length of an arrow, but it doesn't mean the electric field has the same amplitude over this distance. Everything is defined at this point, and this arrow's length is just showing, giving you an indication of the amplitude. Okay.
Professor,
Yeah.
when they're creating these pictures, are they taking into account the forces that the red dots are acting upon each other?
No. Okay, that's a very good question. So take a couple of steps back. Take a couple of steps back. The red dots don't exist. So it's like, hey, I'm gonna pretend the way that what the red dots, let me say this way. So this red dot means that if I brought a charge to this point, it would feel that force. So there is no charge there, but I'm just doing an if-then analysis. That's kind of the whole concept of electric field. There are these test charges that I say I can, if I brought them in here, it would experience that force. Okay. Now, let's say I could bring in 2 test charges or 3 test charges. So I could put a test charge here, test charge here, test charge here. That's legit, right? We can legitimately do that and see how each of them act. And I think this is maybe where your question really meant, was that is this or this is affecting the forces that this guy would have on this guy and this guy has on this guy? And the answer is, if that was your question, the answer is no, because this whole concept of electric field is we are trying to isolate the thing from other things. So if you wanted to see the total electric field, as you guys will see, we would draw electric field for this. We would, you know, if there was another something here, I would put that here, draw an electric field for that and figure out how that's affecting this, and so on and so forth. Does that answer your question? I mean, I've confused.
Yeah, that does. No,
Okay,
that
let
makes
me
sense.
go, and then just in 5 minutes, we'll do some really simple electric field lines, and you'll see what I mean. And you know, I hope some of the stuff I'm like I'm really struggling to, I hope I'm not confusing you guys. I'm struggling how to relay these concepts because it's kind of very notional concepts. I don't know what even word to use at the moment. So because you're doing a lot of if then, you're doing a lot of things like that. So is it real? Is it mathematical? Is it somewhere in between? Okay, so this is where people, this isn't the whole story yet, but this is where people started, like create some graphical visualization of what this thing looks like. Okay, but they didn't stop there. Okay, so this is where we're starting. As they said, shouldn't have done that. They said, actually, I don't know what they really said, but this is, I'm pretending to be them, whoever they were. They said, look, you know, it's more useful, like I have to define this thing here and here and here, here and here, here. Why don't I just link all these lines together? Okay. And this is kind of what you see in books, right? You see these continuing lines radiating out. Hopefully you guys have seen this picture in some book or another, where you have a point charge at the center and you see these lines emanating out. So kind of these lines give you the direction of where the electric field is emanating out. So you might have seen something like this out of a charge. And the nice thing about this is I can visualize if I put this charge, you know, here or here or here, I can always visualize. And again, this is a simple visualization because you got radial patterns out of point charge, but it easily could get more complicated. So it's good to, have this visual of, anywhere I go, which way does the charge get pushed away? Okay, so they've just linked all these vectors that I would have drawn together in a single line. Okay, so that was the first thing they did. And then, but the problem here is that since we did that, we got rid of the amplitude value, right? So we don't, it's like, okay, we gained something because now we see sort of this continuous thing, but we lost the length of the arrow because again, it's continuous. So what people came up with to make up for that or give you guys give us the amplitude is that everybody agreed that the let's see, that the density of lines at any point will give you the strength of the electric field there. Nathaniel, do you have a question? Sorry, you're highlighted. No? Okay. All right, guys. Let me see. Okay. So basically, like, think about it this way, right? If I have a circle, so I'm gonna pick a circle here. Okay. So, or sorry, a sphere. So this is a sphere. R distance away from the charge. Okay, so, and then let's think of another sphere. Say that sphere is 2R distance away from the charge. Okay, if I think of the density of the lines here that are crossing the sphere, what's the density of the lines? Well, I'm going to call it, so I'm going to say, so density of lines at R1. So this first sphere here. Okay, so what's the density there? It's number of lines, the total number of lines divided by the surface area of this sphere. So if I have certain number of lines coming out, I want to know the density at this sphere. I divide the number of lines by the surface area of the sphere. Okay, and that's just, whoops, divided by surface area of sphere. And that surface area of sphere is 4 pi r squared. Okay, so density of lines at R1 is number of lines divided by 4 pi r squared. Okay, now let's look at the density of lines at R2. At 2R. So this guy is the density of lines here in this sphere. And what I'm about to calculate is the density of lines out here. Okay, well, it's got the same number of lines. Let's call it 30, well, whatever it is. It's got the same number of lines that cross this sphere will also cross this sphere. Does that everybody agree with that? I'm just saying these lines are emanating, whether my sphere is here or here, that same number of lines have to cross the surfaces of both spheres, right? Because they got to leave it. Okay, so the number of lines is the same. But then the denominator, the surface area of the sphere though, is bigger in this 2r case, right? It gets much bigger. And that's the equation for that is 4 pi 2r squared is equal to number of lines over, what is it? 8 pi r squared. You get that right? No, 16.
Shouldn't it be 16?
16, yeah, thanks. Never trust my math guys. Okay, I'm gonna somehow get both of everything here. So look at what happened here, okay? So we said now these lines represent the direction and the density of the lines, how dense these lines are, represents the strength of the electric field. So the density of the lines, the distance of r away is this guy, okay, which is the number of lines divided by 4 pi r squared. We went twice as far away, okay, and the density of the lines, so we went twice as far away, the density of the lines dropped by a factor of 4. This was 4, this is 16, right? So, and we went, so if I write this, this is equal to number of lines divided by 4 times 4 pi squared. So when I went twice as far out as this guy, the density of the lines, I went out twice as much, the density of lines dropped by 4 times as much. So it's we dropped by 1 over r squared, okay? So which is the effect we expect to see on the strength of the electric field dropping by 1 over r squared.
Professor,
Meaning that, yeah, go ahead.
can we have infinitely many spheres? Or how many spheres does an E field
Yeah.
have?
Yeah, it's just basically you're thinking as you're drawing these, you can just sort of think about where am I gonna be? You're just thinking about where am I gonna be here. So, but remember, this is a visual map. So basically the visual map is like, just like you wouldn't have necessarily, depending on your topographic, Cesar, are you familiar with topographic maps? I'm sure you've seen them or like.
Yeah, I've
on
seen them
hiking
before,
or
yeah.
something. Okay, so like you wouldn't, it's just a matter of convenience. You could have like an infinite number of lines here, just infinitely close to each other. But at some point you go, okay, I get it, right? I'm getting what I visual I want out of it. I get the feeling that this is like a particularly high point and that there's like, I don't know if you guys are familiar with it, but the closer the lines typically topographically means the slope going up in that direction is higher, and a straight line means that this height is the same. So it's kind of a ridge line maybe and another height. So it's kind of just a visual thing. So theoretically, you could make that as fine as you like. And, you know, as you zoom in, I guess you make it finer. And as you zoom out, you make it less fine. It's the same thing is true here. There's no, this is just like a map that you're creating for yourself. And again, you'll see how this is a little bit more useful. Like right now, we're just describing how it's put together. As the shapes of charges and stuff get more complicated, it's a more useful map. But yeah, I can draw these spheres as close as I want to each other. Okay, and at each point, try to use that visual, but it's up to you how many you would want to draw. Does that make sense?
Yeah, I got it. Thank you.
Yeah. The point I'm making here with these two points is just that thinking of the density of the lines crossing some, so let me draw this like this, keep the distance the same. Like let's say this is How do I do this? It's not gonna help. Now I'm gonna probably confuse you guys more and more, but let me just do it anyway. What the heck? So I'm gonna select this. So I'm saying if this guy was here, notice it's 3 lines are crossing it. If it goes up here, only 1 line crosses it. Do you see what I'm saying? Kind of as a visual. That the density is dropping as I'm moving away from the center, and it's dropping the density of the lines crossing is dropping as, you know, the 1 over r squared as we expect. So, all right. So what else do I want to say? So again, just where the E field is more dense, the more lines there are. And you know, you can do this any way you want. Let's say you said, hey, for every Coulomb, you could say this. I'm not saying we're gonna say this, but you could say for, you know, 1 Coulomb of charge is 32 lines. Why 32? I could make him 9, I could make him 16, I could make him 8, as long as I keep them the same for my particular map. Okay, so it's kind of convenient. This is, does everybody get what I'm saying here? That I could have, I drew like, you know, 8, I don't know how many lines that I drew, ended up being long more than 8. But let's say I ended up drawing this many, and we all agreed that, you know, I'm gonna, if there was a Coulomb of charge here, I would draw 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 lines for a Coulomb of charge. And then as I saw how many of these lines would cross a particular area, that would give me an idea of the electric field strength of that area. Okay, so I could do that, but by convention, now this is gonna seem really weird. Just play along with me mathematically, okay? So by convention, okay, as a convenience, you can think about drawing. You wouldn't draw this number. This is just a thought. Is 1 over epsilon naught of lines. Okay, per Coulomb of charge. And the reason for that is, this is a humongous number. Again, we're just thinking notionally, guys. So the reason for that is, if you think about, like, let's say if I had a charge of Q and I drew 1 over epsilon naught charges, lines, sorry. This would be the density of the lines. Okay, and then I would have the surface area at a particular point. That would be 1 over 4 pi r squared. Okay, so this is the area. And it so happens that this is exactly equal in equation wise to the E field at that point. So if somehow I could draw this many lines per Coulomb of charge, again, this is a humongous number, then I could go look at the density in my little drawing. I could go look at the density of any area, and it would have, that number would be exactly equal to the electric field. Let's just bank that for a second because it's very confusing. So let's just go do something fun for now. So let's do some examples. Okay. Everybody good and confused at this point? No, nobody. Okay, sorry guys. All right, here. So let's do some examples. And this, hopefully this will start looking more familiar. Let's say you had a minus charge and a plus charge. Okay, now again, I'm just gonna draw some real estimates. Like you can go to your book or any book or on the web and see sort of electric field lines for different shapes, different charges, etc. But let's think about what it would look like in this case, right? This kind of a map. So, close to this positive point. Well, let me pick on somebody. Like let me pick on Loe. Ready, Loe?
Yeah, I'm ready.
Okay, good. So let's think about close to this guy. Close to this guy. Remember the electric field has got this Q. So if you want to think about the electric field, has got the charge. It's got this 4 pi epsilon, and it's got this 1 over r squared. And then, so this is the electric field, right? And it's got this direction. So if you looking at this just close to this guy, how do you think the electric field would look like? The electric field lines.
Is it gonna be going from the positive to the negative?
That's true, but like, how about over here? So here you'd have,
It's also
Sphere.
gonna be going towards the positive.
so here you're going to be doing like, how would I draw the line here? On this side.
Oh, Epsilon said it. I guess it curves towards also the negative, the same way
Yeah.
that
Yeah, but just think about it like step by step, because I think you're maybe going, so let's say if we think about it step by step, right? Step by step, you'd kind of like, or at least that's how I think about it. Close to this guy, very close, this 1 over r squared is like a really big number, right? Really close to this guy, you can almost pretend like this guy isn't there. Okay, that there's no electric field line being caused by this guy. Remember, we're talking about the electric field. Okay, so I forgot who I was asking earlier, but when you're looking at the electric field, first you're thinking this guy is not necessarily even here. And then we got to think about the effects of this guy and draw the electric field for him, and then sum it all up in vector notation. So initially, we can think about this guy's far enough of a way. So this guy is generating, if this guy was just sitting by itself, or just for the sake of discussion, let's say this guy wasn't here, okay? This guy was just sitting here. It would have electric field lines pointing like that. You with me, Louis? Is that true?
yeah.
Okay. And if this guy didn't exist, this guy would be having electric field lines sort of the same way, but it's pointing towards it, right? So if this guy would have electric field lines like this, and this guy would have electric field lines like this. Okay, so what would happen is the real electric field line would be this vector plus whatever effect this guy has. So there's be some tiny little vector coming from this guy, because you remember, like, this is far away compared to this guy for a point here. This guy is very far away. So its electric field strength here is going to be tiny, pointing in that direction. This is superposition. So I'm just going to, when I think about the electric field here, first I'm going to think about the electric field caused by this guy. Then I'm going to think about the electric field caused by this guy and add them up in vector notation. So out here, there's a tiny vector coming from that dude and a really big vector coming from this guy. So this guy is not going to have much of an effect here. So the electric field here is pretty much that sum total of the vector is still going to look like pretty much like the vector as if this guy was sitting by itself. Okay, and then the electric field line here directly in between. Okay, imagine if you had a vector here from this guy initially, and then a tiny vector caused by that guy, but they're both pointed in the same direction. So it would just be straight line. And here it would be still be a straight line because the electric field caused by this guy is now big, that vector, and you got a tiny vector from this guy. So I sum it all up. So this guy would be a straight line pointing here. And points in between, like you guys are thinking, is points that are electric field lines that basically go like this. And so, and in fact, to really do this drawing correctly, we would have to add the electric field vectors at any point. So here I would have to draw the electric field vector caused by this guy, add it to the electric field vector by that guy, and it would give me some direction like that. But fortunately, other people have done this. And again, we're just doing an estimate here. And so you'd end up with something like this as your, and remember, this is a map. Okay, so Luay, does that make sense what I just did?
Yeah.
And conceptually, so this is just a map now. Now I could think about, okay, if I had a charge, if I put it here, what would the charge do? Well, it would do this. If I put the charge here, what would it do? Well, it would do that. If I put the charge here, what would it do? It would do that. This is like the usefulness of this map once you've created it. It's like, you know, I don't need to, if I had this, just this situation with the electric charge here, I don't have to go add those vectors. I just got to move it along those contour lines because I can just kind of visually see what they're doing. And then I can see that here, if I put a charge here, it would get pushed out really hard because the electric field lines are really dense here, but they're less dense here. Okay, so if I put a charge here, it's going to initially get pushed really hard, and then it's going to slow down. The push will be less. Whereas if I put the test charge here, it's going to go really small push, tiny push all the way around until it gets around here. So does everybody see the value of these electric field maps? Electric field, you look at the density of how dense the lines are here versus here, and then the direction of the lines. Okay. So by the way, this is called we'll be visiting this thing again. This is called a dipole, which is two charges of opposite, two particles or two entities of opposite charge sitting next to each other. So it's called a dipole, and you'll kind of see it, hear about it more and more, or some here and there. Yeah. So by the way, the test charge is by sort of agreement. The test charge is always considered positive whenever we put it. So that puts it. Let's look at another example. So example, whoops. Oops. 2. Okay, so let's say I've got two charges, but this time they're both positive and they're equal. Okay. Again, the way I could think is close to this guy. Again, we're going to have an electric field vector being caused by this guy, plus an electric field vector caused by that guy, and I have to sum them up in vector notation at any point. But close to here, the vector for this guy is going to be huge. The vector for this guy is going to be tiny because of, again, this 1 over r squared effect. So I can pretty much assume that here, the electric field looks like that, radially away from it. And the same thing goes for this guy, close to here, be going away. Okay. Let's see what other person can I pull into my Jonathan? Good morning, Jonathan.
Hello.
Oh, is right. So think about what would the electric field look like here? If I drew a line here, what would the electric field line look here?
It would cancel. It'd just be nothing.
Exactly. Thank you, Jonathan. Good answer. So you'd have an electric field, this guy, oops, pointing this guy, right at the center would have an electric field line pointing that way. And right in the center, this guy would have an electric field line pointing the other way, exactly the opposite way. So you would have zero here, zero electric field here would cancel out. Okay. And so you like, and this line going up here, right? So basically, again, I'm doing an estimation here. The way you can think of the electric field lines from here, they can't be doing this because I know the electric field line needs to be zero out here. So they're gonna do this up here in the center. So these guys are gonna go this way. And yeah, just think about visually on every one of these points. If I think about like here, whoops, shouldn't have done that. So think of a point here. It's gonna have a very strong vector from this guy, pushing it out like that. And it's gonna have a weaker vector from this guy, but it's still getting pushed out. So this guy, strong vector from this guy and a vector from this guy. So it's gonna go like that when I sum the vectors here. Or you get the idea. So the lines here are still getting pushed out. But it's doing this funky thing in the middle, right? Because if imagine if you put a positive test charge here, it would kind of get stuck. It'd be getting pushed out from this guy and this guy. So here, it wouldn't be able to move here, here. If you put it here, it would get pushed out by this guy more. If you put it here, it get pushed out by this guy here more. And the electric field lines are stronger closer by and they're getting weaker as you move away. Okay, so that's a map of what this looks like. So Jonathan, I have one more question for you, since you answered so well in that first one. So as you move away from, let's say you move very far from this couple, right? So you move zoomed out, zoomed out, zoomed out, so that visually you saw these guys as being so close together. What would the electric field lines look like out here? Good response. So they would look like a point source, right? So think about it. If you're
You
moving
said look
far
like
enough
one.
away. Yeah, but it
It
looks
would
like,
look like one positive charge.
well, it looks like one positive charge of amplitude 2x, right? Because you'd have a Q and a Q. So it looks like you got a point charge of value 2Q. And in fact, if you think about these, again, there's a reason I asked that is because these electric field lines, imagine when we move very far from these. So let me erase this. What would they look like? Here they're doing funky stuff, right? They're moving like that. I'm trying to redraw this. But as you move far enough away here, they look like they're just, again, they're doing the radial thing because these guys are doing. So if we looked at the map and we were zoomed out on the map, so zoomed out up further and away from these two, the further you out here, the more they look like just a single charge. Let's say this distance was, I don't know, like a meter. And let's say you were looking at these two charges from Mars, right? They look like they're just kind of linked together. You could zoom in your map really close by and see there's this sort of weirdness here. But by the time you get to Mars, you just think about them as these two charges, and sort of like on your map, they look like they're kind of like linked together. Just like the way if you look at the map of California, LA, like, you know, Pomona and Pasadena and Fontana and Santa Monica all look like a single point. But as you get into, zoom into the map of LA, you'll see how they're separate. Okay, so this is, again, just a map analogy. Okay, and then let me do one last one before we take a break. And the reason I'm giving you guys these examples is that this is how these guys that came, you know, you see these pictures of electric field lines in your books again, or online or whatever, or maybe you already have some visuals. This is how people made these maps. They went through, instead of doing it like I'm doing it with these estimations, they actually, you know, hopefully with a computer, calculated what the electric field vector would look like on each one of these points as you move far or away. So one last guy is, imagine if you had, this is just to show that we can do this for any charge values, right? So you could have, on this side, you could have twice as many positive charges as negative charges here. And again, you would draw the electric field profiles, okay? Except now you would end up having electric field lines kind of being, drawing them kind of further out. So this guy tends to dominate, right? As you move far enough away from this thing. Now imagine, remember the dipole, when they had the same same and opposite amplitude, these guys it looked very symmetric. But because you have twice as many charges here as you do here, this guy tends to win the vector summation battle as you move away from this guy. Okay, so here again, this guy would look like he would win the vector summation battle here, but as you move far enough away, you would, this guy would win the vector summation in fact. So Jonathan, just to keep bugging you, if you move very far away from this, okay, what would the electric field lines look like, do you think? Like out here?
Singular positive charge.
Exactly, yep. So it would look like as if you had, you know, you had plus 2q minus q, a plus q. So the electric field lines out here would just look like they're like radially going out. Again, just think of it like a map. And the whole idea behind these electric field lines is now you've got a visual and a way of thinking about these things. The closer these lines are, when you look at a map, or when you look at the electric field map, okay, the denser the line drawings are to each other, you know, that's where the field is stronger than out here. And that the direction of these lines tell you how a positive charge would sort of move along these lines. Okay. Another, just one more, sorry, one more case, just because it goes back to our quiz 0, sorry. And let's say if you had a plate, and then you had another plate, and you had positive charges on this plate, and you had negative charges on this plate, the way things would look, again, you're going to do it the same way, but you know, you think about each one of these independently, and then you'd have sort of electric field lines going like this. And around this periphery, they do funky stuff. But here, they would just look like straight lines. So that's like a sort of a capacitor. Okay, guys, that was a lot. Let's take a 15-minute break. And let's get back at 9:30 and keep going.
Hey, Professor, can I ask you a question possibly?
I think he left.
For sure.
Hi, guys. First of all, Nathaniel, I noticed you had some chat stuff. Did your questions get answered from the discussions, or did you have
I
a question?
was
Sorry,
just like kind of answering through the examples.
Oh, okay. So you're good. Okay,
Yeah.
great. So just generally question to the class, we're still kind of officially like going through my massive review as part of our multi-week review. So any inputs? Is this useful for you guys? Am I just boring you guys? Like, is it useful? Where are we at? Is this stuff you guys had seen before?
I remember this stuff, but it's definitely helpful for the review because I don't think I've touched this stuff in over a year. So.
Yeah, okay. Anything else? Anybody go faster, slower? Speak up, everybody. No, somebody? No?
I think
Anybody
you're
else?
good.
Okay. Okay, so we'll go, okay, good. I think, yeah, it's getting like, generally, yeah, I think it's generally good to go over this stuff. Otherwise, I think I know I love, I can't tell you how much I love electromagnetics. I loved it when I took the class, but I don't really use it continuously. I certainly don't use it in this mode continuously of doing, vector calculations and surface integrals and thinking about these fundamental things. So although I really like the topic, I find it, and like just reviewing it to give these lectures was really good for me. Just these real basic concepts. So anyway, hopefully it seems like it works the same way for you guys. Okay. All right. So now, having said that, I hope you guys grab some coffee because we're ready for some math. So what we talked about was the concept of electric field lines, okay, which are a way to basically tell you guys what you're seeing in those maps of electric fields. Now I'm going to do, this is kind of the math part of the class where we're going to, again, this is kind of a warm up for how we do math in this class, or doing some examples of dealing with vector summation and so on. So the idea is, so this is example, which is doing, let's calculate E field for dipole. Okay, so remember the dipole was when you have two charges, they're the same value, but opposite charge sitting a distance away from each other. Okay, that's called a dipole. And so, if we were gonna calculate remember the electric field lines go all over the world, all over the universe. So if we were gonna calculate them for all that, we'd be here for a year or God knows how long and need computers and so on. So we're just gonna calculate them. And then also vector summation and stuff by hand isn't exactly easy, at least for me. So we're just gonna calculate them at a couple of easy points just to get a feel for how these things work, okay, or give you guys, like, remind you guys of vector summation and so on. So first thing we're gonna do is we're gonna put these charges in like a coordinate system so we can kind of talk about X's and Y's and things like that and distances. So we're gonna put a charge plus Q over here at point, let's call this, put this guy on top. So at point X is equal to A, we put the positive charge. That's where it's sitting. And at point X is equal to minus A, I'm going to put a negative charge. Okay, and we could go around calculating the charge, the electric field lines being caused by these two guys anywhere. Remember, like if I was gonna go calculate the electric field line here, I would calculate the electric field vector being caused by Q. And I would calculate the electric field line caused by minus Q. It should be smaller because the minus Q is sitting further away in that case. I would sum them in vector format and get, I guess, something like this. Okay. This would be the electric field line here. So I could do that, anywhere out here by just calculating the electric field line from this, calculating the electric field line vector, sorry. Calculate the electric field vector for this anywhere, calculate the electric field vector for this anywhere, sum them up in format, and that's what give me the electric field at that point, electric field vector at that point. But me being lazy and that being difficult, we're just gonna do it at a couple of easy points. They're still not that easy, but they're relatively easy. So one point is here, okay, right on the x-axis outside. So point, let's call this point 1, point, and just on the y-axis, so point 2. Because I kind of faked this problem, so these two guys are equidistant from the y-axis. Okay, this point ends up being easy. Why? Because I'll have a vector pointing this way, I'll have a vector pointing that way, but because at this point or anywhere in this line, they're equidistant, this charge and this charge, they would tend to get rid of basically, like if I have this point here, this guy, you can imagine like this guy, its component in this direction is going to get canceled with this, these two guys would cancel each other out, and I would only end up in with a horizontal component. And here, because it's sitting in the same line as these guys, the vectors for this guy is going to be pointing out, the vector for this guy is going to be pointing in. So again, I don't have to worry about like weird angles and stuff like that. So hopefully it'll be a little bit easier. But anyhow, let's calculate it. So let's look at point 1. So which is this guy? It's a point sitting in on the x-axis. So any point sitting on the x-axis. Okay, so remember that we have the electric field is Q, whatever is the charge causing that guy. Oops. Are you guys there?
Yeah, but you're not sharing your screen anymore.
Got it. I have to. Let me. Sorry, guys. Nom, 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 nom. Okay. Oh, what happened here? Okay. So remember the electric field profile at any electric field vector at any point is Q, the charge that caused the electric field. Again, that could be plus or minus depending on what Q was, over 4 pi epsilon naught 1 over r squared, which is the distance away from this charge Q and in a direction sort of TBD. Okay, so it has to have, this is like an amplitude, and this is the unit vector direction. Okay, so let's look at it here. So, and so that's one, okay? And then the force, remember that force is the electric field. So this guy times the charge being acted on. So call it Q2, call it whatever you like. So that's the force, okay? And that also remember the superposition principle means that like the superposition principle says I can calculate the electric field from this guy. And then I can calculate the electric field from that guy and sum them in a vector format. Okay, so let's look at it. So electric field at this point, again, at this point X, that guy is Q. So let's figure it first from okay, so it's Q over 4 pi epsilon naught. Okay, remember that it's just sitting here, and because we faked it so that it's on the horizontal axis, it's only going to have component facing this way and this way. Okay, so we would have 1 over x minus a squared minus 1 over x plus a squared. Okay, it's going to be, let's call this guy I, and let's call this guy j, the directions pointing that way. So it'll just be sort of the unit vector pointing in the I direction, which is that guy.
Where does the second term come from? The x plus a?
That's the contribution from this guy.
Then it would be 2a, right?
Well, think of it this way, though. You're talking about you are, let's see, is it 2a? I was thinking about
Because
the
of the
same thing.
distance.
Is that guy? Is it 2a? Is it 2a?
If X is the distance from the point to the center, then it's not, it's just 1A.
No, x isn't x the distance between
We're talking about this distance?
no, you're right, you're right. Yeah, you're right. You're right. I thought x was the distance between point like positive q and endpoint 1. You're good, you're good.
Yeah, okay, good. All right. Okay, so we got this guy basically. So now we want to let's start moving stuff around. Okay, so we will do, let's see, what am I gonna do? So I'm gonna move the I over here, Q over 4 pi epsilon naught. Okay, so we'd have x plus a squared minus a squared over squared minus a squared squared. Guys, did I skip too many steps there? Were you okay with that? Okay, basically I multiplied both sides times, the x plus a squared. This guy, that guy, so I could put them in the same denominator, and that's what things ended up on the top. So this guy, maybe I should go step by step here, is gonna be x squared plus 2ax plus a squared minus x squared e plus 2ax. Is that right? Minus x squared. Now let me just do it this way. Hold plus a squared. So I'm just calculating this now. So this guy would go out. This would get canceled out and it would end up with 4ax. Okay, so then you would end up with iq over 4 pi epsilon naught 4ax over x squared minus a squared squared. So this is formula for E field. On x-axis for dipole. Okay, and then we can, yeah, go ahead.
Just scrolling back up to your first equation, you have 1 over x minus a squared minus 1 over x plus a squared. Do we know the location of 0.1, or how are you saying the radius is equal to x minus a squared?
I'm saying for if I pick any x here and I plug it in here, okay, it would give me the electric field at that point x. So for example, I picked, in my pictorial, I picked x here. Let's say I actually was here. Right, it would be 0 minus, so this would be 0 minus a squared. So this would be 1 over a squared. And this would be 0 plus a squared. So it'd be a squared. So it'd end up with 0 electric field here. Because you'd end up with this guy and then this guy being equal and opposite. So I can move this x around anywhere the way it's set up and it would give me the electric field there. Does that make sense?
Yeah, so x doesn't have any constraints besides the fact that it has to stay on the axis, and then a would be some constant that's on the x-axis.
Yes, yes. Yep. So what A is doing is it's giving you like 2A is the separation between these two dipole, the two charges in the dipole.
Got it. Thank you.
Sure. Okay, so that is the formula for this beast. Okay, now let's think about it now. So this is the exact formula, let's call it. And mostly, the idea why we're doing this is because I'm trying to demonstrate a couple of things. One of them is like how this, as we're talking about this, is how this works, right? The vector summation. And of course, like I mentioned, we're picking an easy point because it's on the same line as the dipoles. I'm not doing any trig things with the vectors. They're lined up sort of on top of each other, so it's easy to sum them. But I'm also still keeping track of the electric field direction using this I vector. Okay, so that gives me some exact number. So that's the first thing we're looking at. The second thing we're looking at is like, okay, now what do I do with this? Okay, or how do I think about it? Well, one thing that you'll see me over and over again, just like we did a second ago, like saying, okay, well, does it make sense if you look at the electric field here, that they would cancel each other out and this would be 0? Okay, good test case. Okay, the other test case could be, hey, what would happen if I'm very far away, right? So let's say if x is much bigger than a, what would happen? Okay, so this is far away from dipole on x-axis. Okay, so this would be this electric field. Now we're talking about approximately, because what I would say is, I'm gonna copy this over. And so if X is much bigger than A, then I can just say like this, that guy, I don't really worry about, right? Because X is gonna trump it. So it would end up approximately IQ 4 pi epsilon naught for A over X to the cubed. I get that right? Yeah. Oh, these guys will cancel. Let me erase those. There's fours. Let me actually write it a different way, which seems idiotic, but actually I see now this is, so I'm just gonna still leave a 2 here and a, why am I doing this to myself? No, let me just leave it for the sake of discussion like this now. E over X cubed. Okay, so this basically tells us, what does it tell us? It tells us that the electric field on the axis far from the dipole. So when X is very high, very like you're way out here, right? You're out here, the electric field is dropping off. Remember, the electric field due to a single charge dropped off as 1 over distance squared. But because I have a charge, but then I have an opposite charge that it's actually kind of weakening the electric field that's being caused by this guy because it's opposite. So it's pulling opposite to this guy. So it's weakening the electric field faster in the case of a dipole than just a single charge. So if this was a single charge, we would have something like 1 over X squared. But when you have, because we have this opposite charge in this pair, it's weakening the electric field further. And we're actually, the electric field is dropping off much, much faster in that horizontal direction to the dipole. Okay, everybody with me? So that's sort of the effect as we're looking at the electric field in the x-axis. And then coincidentally, this is where the math, another bit of math torture comes in. I'm just going to have this as an aside here, because there's this dipole. You'll see this dipole periodically. Okay, it's used in examples. It's used in real devices and stuff. So what they have is they call something, it's called a dipole moment. So this is a definition for later. So I'm not doing much with this guy right now. Dipole moment. And that's defined. So it's P is 2AQ. Okay. So remember, a dipole has 2 charges that are equal and opposite. So that's the charge of the dipole. And they're separated by a certain distance 2a. Okay, so the dipole moment is the charge times the separation. Okay, it's a dipole moment. So if I look at the electric field, for example, in this case, so E field at X, so much far from the dipole in the direction that the two charges are lined up. Okay, so the electric field would look like approximately I times P over 2 pi epsilon naught x cubed. So this, almost bank this on some bank of your head. I haven't done anything different. I've just kind of made this definition of dipole moment. We don't know why, but again, because we run into this dipole again and again and again and again, people, defined this 2AQ that's in your equation somehow, so that they talk about moments. So we'll come back to that, I'm sure. Okay, but just thought I'd mention that in case you guys we're not really using it. I'm okay with being with like that at the moment. Okay. So any questions about what we just did? No? Okay. So now let's do the calculation at this point 2, which is slightly less pleasant, especially if we don't like trig. So point 2. Okay, so let me copy this guy. Is it wise to copy it? Nah. It's not. So we're at plus A and minus A. Plus A, we got a plus Q. Minus K, we got a minus Q. And this guy's Y, this guy's X. And we want to calculate the electric field anywhere on the y-axis. Okay. So again, we have the reason I picked y-axis is we have this positive charge is going to have a vector pointing away from it, the electric field for that guy. The negative charge is going to have a vector pointing down towards it. But because this distance is going to be always the same on this y-axis, they are going to this component and this component are always going to cancel each other. So when you're sitting on the y-axis, you're only going to have a horizontal component, okay, which is convenient. Live has stopped due to having stopped screen sharing. Okay. Great. Why do I keep stopping screen sharing? Oh, I think I dropped my connection. You guys can still hear me?
Yeah,
Yeah,
and I can
somehow
see a frozen screen.
yeah, my iPad dropped there. Why is it dropping there? Let me just see if I'm on Wi-Fi here. Maybe that's why. Somehow I only ended up on LTE. Let's try this again. Okay. Okay. So where are we? Here we go. Okay, so I don't know how much of you guys, so much of the drawing you saw, but I have a vector from the positive charge, vector from the negative charge on this axis. This vertical components completely cancel out by definition. So you end up only in the horizontal component. Okay, so that's why we picked that as an easy point along this y-axis. Okay, so let me define one more thing. I'm going to define an angle theta that's the same as this angle theta. Okay, so if I look at the electric field being caused by this positive guy, it's going to be, where are we? Let's keep it with purple. E is minus I. Well, let me keep it this way. So I'm going to now look at just this component of the electric field caused by the positive charge, right? I'm just gonna look at this guy because I talked myself into saying this guy got canceled by this negative guy. So I'm just gonna look at this guy. So it's that guy is gonna be pointing in this direction. Earlier, I defined this I as pointing in that direction. So I'm gonna have the electric field, the vector direction is gonna be minus I. That's the unit vector pointing in that direction. Okay. Then the charge is Q over 4 pi epsilon naught. And now this, I need my 1 over R squared from here to here. So this is A. This is Y. So this 1 over R squared is gonna be 1 over square root of Y squared plus A squared squared. Okay, that's this guy. Times cosine of theta, because I want to know what component of that is lying in this horizontal direction. Okay, so this guy now, because it's x squared, sorry, 1 over y squared plus y squared. Y squared plus a squared square root of squared is just y squared plus a squared. Okay, cos theta. That's what I end up with. Everybody with me? So
Yeah.
that's just the horizontal component of the electric field caused by this guy on this y-axis, cos theta. And then also cos theta, cos of theta is is this guy over that guy, right? So that is a over a squared, well, over y squared plus a squared square root of. Okay, so trig comes in, a over that gives me the cos of this angle. So I plug that in. Okay, so I end up with minus I Q over 4 pi epsilon naught A over y squared plus a squared to the 3/2. So I just went multiply this by this, ended up with that to the 3/2. The A, whoops, the A just moved that here. Okay. And now if I want to, so that's just the electric field coming from this positive guy. So I'm going to call it, I don't know, plus Q or something. So if I want to do the electric field total, okay, this guy, this dude just does the same thing because it's pulling in this is the horizontal component of this guy and this guy just on this axis are the same. So if I want to do the total, I just multiply this thing by 2. This is what happens when you fake a problem to make it easy. And that's what I come up with. Okay. So that's what you get for the electric field anywhere on this y-axis. Okay, so what does it tell us? Well, it's oops, didn't draw it. So it's giving us the direction. Notice it's giving us the direction of the electric field. It's always pointed in this direction, no matter where we go. And it's got this sort of relationship to the values of y and a. So again, if you look at at y is equal to 0. Okay, now you don't get a 0 value, right? Because this guy is pushing charge and this guy is pulling on the charge. So at y equal to 0, you end up with, what do you end up with? You end up with minus I 2q over 4 pi 1 over a squared. That's what you end up with. So you end up with, yeah, you end up with this electric field here pointing in this direction. And if you go to y much bigger than a, so now we're talking about approximations, you get minus I 2q over, whoops, 4 pi epsilon naught e a over y to the third. Yeah. Is that what you got, John? Yeah.
Yes, sir.
Okay.
That's what I got.
Okay, awesome. So again, we see that if you are going far, so again, you're just on this axis. If you're going far, far, far out here, away from these two guys, again, the electric field is dropping off as distance cubed. So again, because you have this negative charge, sorry, this negative charge here is further weakening this positive charge as you go up far away. So it's not dropping off as distance squared, it's dropping off as distance cubed. Okay, so we can do, and in fact, well, I think, sorry, I haven't assigned or, suggested homework problems because you don't have to do them, but it's strongly suggested, but I haven't actually suggested what they should be. I'll give that, but you'll end up doing, you can do problem after problem like this, and it's sort of a similar concepts. What you end up doing is start from you always have this really simple equation. No, not that one. You always have this simple equation for electric field that you're working with. And the rest of the task is doing, calculating the vector directions and summing things up in vector dimensions. And usually these hand problems, believe it or not, they're sort of geared up so that you can do them with, enough trig, etc. So anyway, so that's just a field at a couple of points. We could just go on and on, trying different things. Let's do another example. Any questions from that, by the way? What we were just doing? That was just an example of calculating electric fields with vectors and so on. So let's do another one. This is a little bit more dynamic, should I say. Okay, so let's say you have two plates. One of them is positively charged, sort of uniform charge on the positive side. The bottom one is negative charge. So we anticipate that the electric field lines are going to go like this. Here. Okay, and then let's say we have a charged particle. And we're going to launch this charged particle with a velocity v. That's like in this direction, right? Perpendicular to the electric field into this plate. Okay, and then we want to see what happens. Okay, so now I think I'll spare you guys. Let me just say let's think this through, right? So one is, let me just bug somebody. Anybody want to help me with this?
Sure.
Okay, great, thanks. So let's think about it. You have a particle with velocity going this direction, and you have electric field going in this direction. So what is the force that this particle would see? For a second, forget about gravity. What would be the force that this guy would experience? What direction would it be?
Do we know if the charge is positive or negative?
Let's call the charge positive.
If it's directly in the middle between the two plates, I think the charges should just all repel. But so it should either feel nothing or slightly go towards the negative charge because it's being pushed down by the positive and being attracted by the negative.
Yeah, but so if you think about this guy up here, right? You're thinking about this guy could be here, this charged particle here, here, right? Think about the force on it. And so you can think of the electric, these are electric field lines, right? And the force is electric field times the charge of this guy, charge of our particle. Okay, so now if you have a situation like this on a positive plate and a minus plate, this electric field line is gonna be constant here, right? One, well, you could, for whatever reason, I guess I didn't draw it that carefully. You can see the density of there's no reason the density of the lines would change, right? The other way to think about it is out here, this guy would have a very strong vector pointing this way. And this guy's vector here would be smaller, but they're pointing in the same direction. Over here, the vector from this guy is going to be small, but the vector from this guy is going to be big. And here they're going to be equal strength. Okay, but it turns out the electric field line is going to be constant all the way through here. So the force, like regardless of whether the particle's here, there's only going to be a force pointed on it. The force is going to be pointed down, and it's always going to be the same force, regardless of whether it's up here or down here. Does that make sense? Qualitatively?
Why doesn't the force get stronger as it moves closer to the negative side?
So think of it this way, as you move closer to the negative side, as you move here, right, you get a stronger force pulling it from the negative charges here, but the force gets reduced from the positive charges here pushing it. It's always the positive charges on the top plate are always pushing it down, and the charges on the negative plates are always pulling it down. And so the direction is always directly down, because if you're a positive charge, this guy's pushing you down, this guy's pulling you down. The total vector summation is always going to be down. And up here, this guy's going to be pushing you hard. This guy's going to be pulling you down weakly. Here, this guy's going to be pulling you down strongly, but this guy's going to be pushing you down weakly. But when you sum those two vectors are going to stay constant, throughout this separation. Does it qualitatively make sense, or it still doesn't make sense? Why here? Like you're thinking, as I'm moving closer to here, this minus charges are going to pull this much harder, right?
Yeah, that makes sense.
Yeah. But remember that these guys are also pushing it just as hard, like here, right in the center. This guy's pushing just as hard as this guy's pulling. And then that ratio changes up and down. But in sum, they're always doing the same thing. So you feel a force pulling you in that direction. But I think this is where you were going, is also there is no force in this direction. Right? This electric field, there's no force. If we assume there's no gravity here, this guy doesn't feel a force in this direction. Okay, so generally what happens is, so remember velocity. Well, remember that you only get acceleration when there is a force. Okay, so if there is no acceleration, there's no change in velocity. So meaning that your velocity in this direction, there's no force in this direction, right? Horizontally. So this velocity in this direction doesn't change. So it's going to be going by here with the same velocity. But there is a force in this direction, which means the velocity in this direction will change because there'll be an acceleration in this direction. Initially, the velocity in this direction is 0 because this guy's just shooting like this in. But as it goes down here, it's going to be having a change in velocity pointed down. So it's going to have a trajectory like this. Okay, so it's going to keep going fast, still going to keep its velocity going in that direction, but it's going to move down. Okay, just you can think of a similar thing with like a bullet. I don't know if you guys are remembering. So if you shoot a bullet, the velocity in the direction you're shooting at stays the same, but then it starts getting pulled by gravity. So the same thing happens with this positive charge, is it's qualitatively, it's going to have some kind of a trajectory like that. Everybody with me?
Yes, sir.
Yeah, that makes
Okay.
sense.
Okay, cool. So now we can kind of figure out where, like an equation for this. Okay, so again, so let me just write down what I just said verbally. So there's a force here. Okay, and that is the, so the electric, let's just, so I'm gonna say, write down what I just said. Okay, so that the electric field is constant. It's E sub 0, and it's always pointed in the minus J direction. So that's J minus J. Sorry, guys. So this is I. This is J. Okay, so it's always pointing down. So it's always in the minus J direction. And this I and J stuff is just like convention, or like it's just stuff that I'm making up as I go. But if I have a constant electric field, pointing down is going to be minus J E0. Okay, so the force is going to be the electric field times the charge on my particle. So it's going to be minus J E0 times the charge on the particle. And force is mass times acceleration, always. So let's say that my charged particle has a mass of m. So it's going to have a, so sorry. So if I want to say MA is minus J epsilon naught Q. Remember, I'm trying to figure out accelerations and velocities and distances. So I changed the force, use this equation to put acceleration on this side, so that then I can get acceleration is minus J E0 Q over M. Okay. So that's going to be the acceleration. It's pointing, the only acceleration we have is pointing in this direction, at the minus J direction. This is what that's saying. Okay, now let's remember, I'm just going to put a sidebar here. Remember that the distance is distance plus velocity times time plus 1/2 AT squared. Okay, just reminding you guys of, you know, all this sort of mechanics. So let's say, so assume we set origin here. And so starting point R, we call R0 is equal to 0. Okay. So what we end up with is, so R is 0 plus, so I'm talking about, so this is, sorry, I wrote the origin wrong. The origin is here, right? So I'm talking about this is R0 here. Because I'm going to calculate this. Okay, is 0 plus V0 of t times t minus 1/2. I have acceleration from here. I'm going to plug that in. J t squared. Okay, so as time increases, this guy is going to be moving, getting accelerated this way. Okay, so basically what we can do is figure out the trajectory of this particle. At any point, we just plug in a t, right? T0, T1, T2. And then we can basically figure out where this guy is going to end up. Okay. So that's kind of an example of how you can use this electric field to figure out, like, on a moving charge. Okay. So then let's look at another example. Any questions about that, guys?
What's the application or purpose of knowing like where a charged particle ends up?
Well, used to be I had a really good answer for that because I'm an old dude. So, well, and a good example that everybody would recognize. So I don't know if you guys have even heard of like TV tubes, like television sets didn't used to be diodes. They used to be actually cathode ray tubes. And this is how they would work. You would have an electron beam that you would create, and you would scan that electron beam in the back of your TV screen, and it would hit the phosphorus in your TV screen and like light up. And that's what be your television set back in the day. Okay, so we no longer have that example. So right now, you know, people use this kind of thing for in like these particle accelerators and stuff like that, where they create electric fields and they're seeing how far, the way they can tell the mass of a charge, okay, or the charge of a charge is by how far it's deviating, you know, given a certain velocity, it's deviating from, like, where does it come down? From that, you can tell the mass of a charge or the charge of a charge. Basically, you can kind of investigate what that charge actually is. Have you guys, I'm sure you guys have heard of these particle accelerators that, you know, they smash stuff and shoot them through these things. And I'm sure there's a lot of other examples, but I can't think of too many. Does that answer your question?
Yeah, that
Yeah.
answers my question.
Yeah, it used to be so easy. I hate, you know, sort of sometimes technological innovation is a bad thing because it takes away our examples. Can you guys imagine like creating such a thing? Like created an electron beam and moving it around with electric field plates. It's just like, anyway, but people used to do that. And in fact, I'm in San Diego today. There was a huge Sony plant here in Rancho Bernardo. That's what they made. They made television sets. They made cathode ray tubes. So I remember they started shutting that place down like in the late 90s, early 2000s. But anyway, okay. So I'll give you guys another example. This is gonna be.
Professor, can you scroll up real quick? I didn't
Sure.
finish the answer.
There you go.
A question.
Uh-huh.
So, we know that from the electric field, we have a J component of the acceleration, but do we have any J or X or I components for the velocity?
Yeah, as time goes on, you can basically get the velocity is going to be a matter like, so you have a velocity in this direction and a velocity in that direction. The velocity in this direction is going to change with time because of the acceleration in this minus J direction. And as time goes on, that velocity is going to get, the velocity in this direction is going to get higher and higher and higher and higher because there's a constant acceleration on that particle. Does that make sense?
Yeah, thank you.
Yeah. So again, like this is, what is this example trying to demonstrate? I think this example is trying to demonstrate the fact that when we're talking about, electric fields, it's related. Basically, what we're talking about is forces, and the upshot with the forces and acceleration. And a charge, I guess that's the upshot. After all this discussions of electric fields, blah, 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 ultimately what we're talking about is an acceleration of a charge one way or another. That's the real effect. Now, it's, boy, trying to think of philosophically what to tell you guys. So, okay, what is real? Right here, this is a real effect because we're seeing a moving charge and it's easy to visualize, right? You've got movement, it's easy to visualize acceleration. It's easy to visualize force and electric field in this kind of situation. Okay, relatively easy. But, say, when you guys have a capacitor, a parallel plate capacitor, which is where most engineers directly run into like electrostatic fields or current running through a line or transmission lines. We'll get into Maxwell's equations, transmission lines, antennas, all those kind of things. There's always this acceleration from electric fields, magnetic fields, and so on, but it's harder to visualize. But that's what's really going on. Anyway, that probably confused you guys more than anything. But anyway, that was sort of like the purpose of this example, because I think here acceleration is easy to visualize. But that's where the rubber meets the road, is force and acceleration. Concepts like electric field, etc., is just easy, makes it easier for us to like visualize. I don't know about you guys, but at least when I see a parallel plate, I can visualize an electric field going from one to the other. And that helps me visualize what a positively charged particle would do moving through here. Okay, so it's kind of a visualization tool. Things like electric fields or electric field maps, but a very important visualization tool. Okay, so let's think about another. So hopefully I'm not confusing with you guys with these these thoughts. I'm just trying to like, I'm groping here and there to try to give you guys some context or some feel for what we're ultimately discussing. Okay, so anyway, so let's talk about another example, hopefully another visual. Force of uniform E field on a dipole. Okay, so let's say we have a constant electric field in this direction, just in the horizontal direction, okay? So we have an E field that's constant amplitude and it's just pointing in the direction of I. It's pointing in that direction. Okay, so it's gonna, this is what it's gonna look like in equation form. Okay. Everybody comfortable with this, by the way? Hopefully you guys have all seen this. This is this kind of stuff that is exactly what was like bothering me when I was an undergrad. Like, this is like a really, really simple statement. It's just saying that there's a vector, which means it's got an amplitude and direction. I'm separating it into a direction and just an amplitude. Okay. Again, this used to confuse me. Hopefully you guys are all on with this vector formation or notation. Okay, so now let's say we have a dipole. Remember, dipole is a plus charge and a negative charge separated by each other by a distance of like 2a. Okay, so let's say this dipole is, for example, sitting like this. So let's say its center is right here. It's got a so the positive side is up here. So this is A. This is A. The minus is sitting here. So it would get a force pointing, of course the plus is exactly in the wrong place. So it's getting a force pointed the plus side. So remember, this is just a plus charge and a minus charge sitting on, you can think of it on sitting on either end of a stick. Okay, so you have a stick. On one side you have plus charge, on the other side you have negative charge. So this top of the stick up here, it's gonna get electric field, sorry, you're gonna get a force Q E0 pointed in this I direction, right? So QE0, or I could, if I wanted to put force is QE0 times I. And this bottom side of the stick would get pulled in that direction. So the electric field is constant for everybody, but because this is a positive charge, that constant electric field is pushing that guy out and this guy in that direction. Okay, so this guy's getting a minus Q E0 I as a force in that direction. So if you guys kind of look at my video for a second, like imagine if you had, put this coffee away here. So imagine I got a negative charge at the bottom of my pen here and a positive charge, and this is sitting in this electric field. So the electric field is going to push on this guy going that way, pull on this guy going this way, and notice what's happening if I do that. This is going to start rotating.
Like a
Okay.
compass.
Like a compass, exactly. Okay, and it's gonna, think about what it's gonna do. If it's sitting here, it's gonna have a very strong push this way, and it's gonna go here. And at this point, you're pushing this, I'm pushing, pulling that way, and I'm pushing that way too. So it's gonna be a stable point here. Electric field, it's gonna be a stable point here. It's gonna have a lot of force on it to rotate here. Okay, so by the way, I'm really bad with this, with mechanics, but a rotational force is the equivalent of that, or maybe it's called a torque. Okay, so if you think about in terms of torque here, we're gonna have a lot of torque up here, not so much, there's zero torque here. It's gonna be a stable point here. Okay, so let's look at that. Okay, so, oh, before I go into that, so now notice another thing, because if this guy's sitting, I'm like, again, look at my pen. This guy's getting pulled here, this way. It's getting pushed that way, okay? There is no movement of this guy here because, so what, there is a torque that's rotating it. The force is rotational force, but there's no force pushing this whole thing. Because remember, these two guys are connected together. There's no force pushing this guy horizontally because just as much there's a force on this guy pushing it horizontally, there's this point pulling it this way. So my point being, there's no movement. This guy isn't gonna go floating by. It's just gonna rotate. Even if I'm not, even if there's, I don't have a finger holding this point, right? I'm holding the center of it, my finger. But even if my fingers weren't there and this was an electric field and charge, this would not move like this. It would just rotate. Okay, so as everybody get that? Because now we've connected these two guys together. Okay, in this dipole, they're physically connected. Okay, so let's think about what the torque is. Okay, so tau is sort of a symbol for torque. Okay, so that's sort of the rotational force. So that is going to be to Q epsilon naught. Why is it 2? Well, I got a force going this way and a force going that way. So that's where the 2 comes from. And, okay, the torque is going to be always sort of going in this direction. So we got to think about it in terms of theta. So 2Q epsilon naught sine of theta times A. Okay. So that's the torque on this dipole, which means that that is the sort of the force pushing this guy rotationally down here and pushing it this way. Okay, so it's going to take this dipole, try to force it down here, force it up there, and straighten it out. That's this, what's this torque doing? Okay, but again, this whole thing isn't going to want to drift over because these two are connected and the actual force is 0, but there is a rotation, there's a torque rotational force. So there's a torque is the only thing on it. So that one is equal to, so remember there's a dipole moment, which is 2QA. So this was a definition. We gave this definition. It's just verbiage. We you know, if you, when we're talking about dipoles, we just said, okay, the moment is called 2AQ. So we just substitute that. And so we end up with the torques being P, the torque being PE0, P again being the dipole moment, E0 being our constant electric field times sine of theta. Okay, so think about it this way. If theta is equal to 0, okay, theta being 0 means our dipole is lying like this. Okay, that's a stable point. You're getting We're not getting any rotation here. So sine of theta is gonna be 0. So we're gonna have torque is gonna be 0. Okay. If theta is pi over 2, then sine of theta is gonna be 1. So torque is gonna be P times electric field. It's gonna be like the maximum torque when your dipole is sitting like that. It's gonna have a lot of rotational force on it to rotate. Okay. What else do I want to say? And sort of in fact,
Quick
yeah, go ahead.
theoretical question.
Uh-huh.
If so, what if the angle's at negative 180 instead of 0? Like if the positive is all the way over on the negative side and the negative side is all the way over on the positive side. Because
Then
there
it should
wouldn't,
still
there
be-
wouldn't, yeah, there wouldn't be any balance. It would still be trying to rectify, but it,
Yeah,
Can you
yeah,
repeat the
yeah.
question?
I think the question is, if you had the positive here and the negative here, and the electric field is going like, is this the question?
yeah, that is my question.
Yeah. Let me draw it for you.
Nothing-
Let me draw.
it-
Yeah, go ahead. Sorry. Go ahead.
Nothing would happen, right? Because we don't have like a what's the name? We don't have an angle where the torque can affect the particles, right?
Mhm.
So it
Well-
wouldn't rotate.
Yeah. Well, yes and no. Give me a minute and I'll show you guys what I mean by yes and no. So hold that thought. In fact, we can, let me just say one more thing. No, hold that thought, because it's a very, very good question. The answer is gonna come. Uh-oh, are we getting close to being done? Are we done
Yeah,
at 10:45?
Yeah, we have 3
Yeah.
minutes.
Yeah, that's just when you're having fun. Okay, let me guys tell you guys the punchline because of the question. Okay, and we'll get back to it. So the next step we're gonna go through is going to use this concept to discuss the concept of potential. Okay, and just don't, this is just for your amusement because we asked the question. So looking at the potential and looking at the electric field, which is kind of like the potential is the potential ends up being the, what is it? I guess it's the derivative. No, the potential is the integral of the electric field, okay? Or the integral of the force. So what it would look like if I draw it for you guys, the potential. Let me just draw it of this dipole. So I'm gonna draw you guys the potential with respect to theta. So potential is how much sort of energy you guys can translate, how much, I guess when you think about kinetic energy versus potential energy, this is how much you've got sort of stored. So this might not make any sense until we do the equations, but if you look at the potential versus theta, the potential of the dipole, you'll see that it's got a curve like this. So it's like it's gonna look like a cosine theta when you look at the potential, okay? This torque is sine theta, ends up being potential, just take my word for it, is sort of a cosine theta type of function. So you would end up looking like this. It's got a minus cosine theta. So if theta was at pi, and this is theta equal to 0. So think of it this way. So this might confuse you guys more. So think of the torque as being what's left after this, right? So here you have all torque and no potential. Okay, here you have potential, here you have potential. Okay, potential energy. Think of it in terms of energy, right? So at pi over 2, at pi over 2, you're vertical to the electric field, means that all the energy, I guess is one way to look at it, is everything is torque. Everything's pushing you, pushing you, pushing you. Here you have the minimum potential when your theta is 0. Here at pi, which is where you're thinking at pi is when this thing is flipped, you have your maximum potential. Okay, and again, like, sorry if this doesn't make any sense because I haven't defined potential and all these kind of things. But it turns out that this is a stable point, okay, where the plus is here. So like you can think of, if you can think of this as height, right? Imagine if you had a pebble, the pebble was sitting here. If there's some movement back and forth here, this thing just kind of like rings around. So that's the pebble. The equal analogy would be the plus is sitting like that. So if you got any kind of movement here and here, the pebble would just move around. Here, the pebble is sitting up here. It's a stable point. This guy is a stable point, but any kind of small movement, any kind of a small noise would make it pick up a lot of movement. So here you were right. Sorry, wasn't quite catch who was responding. It's a very good point that this is a stable point in some extent with the plus and minus facing this direction, but it's storing a lot of potential energy at this point. Any disturbance here would flip this guy right away. So it's sort of sitting at the height of this potential, and any change here would make it completely flip in this direction. Whereas this point is very stable. I don't know if that helps you guys visualize.
Yeah,
This
that does.
minus
Thank you.
Yeah, sure. And then we're gonna go, I'm sorry, I speak and I'm like, I guess maybe I get this. Anyway, we're not moving as fast as I'd like, but what I was gonna go do is define that potential, and then we would draw it and see how it would look. And it would exactly answer your question. Okay, guys, any questions?
Yeah, Professor, can you post this recording just so I could review it before next class?
Sure, I'll post, I'll post this and the other one too.
And as of now, and as for you, next class is in person, right?
The next one's in person, yeah.
Oh, nice.
All right, guys. Yeah, go ahead, sorry.
Will you be recording your in-person classes?
Yeah, I was thinking about that. If I got a GoPro, and so I was thinking, I don't know how it's gonna work. I've never, I'm always kind of sitting next to my. So anyway, long story short, I was planning to bring my GoPro in and ask one of you guys to like hang on to it or something. It's got a wide field of view, so, but who knows what it's gonna look like, because I'll be doing the stuff on the whiteboard. I don't know if you'll be able to make out the actual equations or whatever that I'm going to write, and I don't know how well it's going to pick up the audio. So no guarantees, but I was going to bring my GoPro and try to record.
Would you be open to the idea of using the projector and your iPad and then just doing a screen capture?
Yeah, that's what I was gonna ask as well.
Yeah, I'm actually fine with that. It's easier for me. If it's okay for you guys, I'm certainly happy with that.
Much better.
Yeah, for
Yeah,
example, because so what we're seeing here, you can actually project it and record it at the same time.
Yeah.
So that will actually work better.
Yeah, I'm very happy to do that if there's no objections. Yeah, whatever works for you guys. I'm an old guy, so I always prefer to sit rather than stand. So. Cool. Okay, guys, that would solve that problem.
Thank
Cool,
you.
guys. So see you guys next week.
Have a good weekend, Professor.
Take care.
Um,
Bye.
I do have a question.
Uh-huh.
Just like at the end.
Go ahead.
So okay, so I took 3200 with Dr.
Uh-huh.
Olson, and I kind of like really fell in love with the subject.
Uh-huh.
So how or what does it take to be part of like Forza?
Yeah, so you know what you can do? I remember, sorry, you sent me an email and I'm like,
No, you're fine.
getting stressed out. Why don't you send me your resume
Okay.
and I will be happy to pass it on
Correct.
to my friends there. So yeah, I'd be very happy to do that. If you want, what we can do is if you want to send me, we can sort of arrange like maybe we can have a 15-20 minute call or yeah, or sort of office hour thing, and then we can talk. I can give you some background about Forza and get some of your background so that I can kind of tell the guys something about you when I forward the email and all that stuff.
Yeah, that's what's gonna be my next question. Like, because other
Yeah.
than what the website says,
Yeah.
I would like to know a little bit more of what Forces does and everything.
Okay, sounds good. Yeah, I'll be happy to give you a data dump on what they do, and then yeah, be
Cool.
happy to
Now,
do that.
so the last question really quick.
Sure.
If let's say that I do like get like an internship or job there, does my senior project have to reflect what like something that I will do there? Because like
Ooh,
Dr. Olson didn't have a team this
I
semester,
see.
and I was really looking forward for it. And I
Yeah,
think I emailed you about the senior
yeah,
project.
yeah, yeah,
So
yeah. I don't have an answer for that because I'm not like a regular Cal Poly prof, so I don't know what your senior projects can and can't have and how they relate to internships. So
I see.
I'm not sure.
Okay. Yeah, I'll probably ask our 4810 then. If probably get more information about just that little point at least.
Okay.
Okay, awesome, Professor. Thank you so much, and I'll send you the resume as soon as I like finish it.
Okay, sounds good.
Thank you.
Okay, thanks.
So I had a quick question.
Yeah.
It's in regards to the torque. It's rotating in the clockwise direction. So do we need to include a minus sign with the magnitude of the torque?
Yeah, I believe you do. I think you're right. Let me think here. Do I need a minus sign? So you're saying the torque is going this way, and do I need a minus sign?
Yeah.
Yeah. Let me think about that one. Let me think about it because it's well, let's think about it this way. So let me see if I can come up with this. So if I was gonna write this torque in vector notation, it would look like the torque would be the dipole moments vector sort of cross the electric field vector. So this would give you let's see what this would be, the right hand rule. So let me think about this. Do I want to do this? Let me see. So so the dipole movement would be in that direction, electric field. Let me think about it, what it would mean in that form.
Okay,
Because
sounds
I'm
good,
gonna,
thank you.
I'm worried I'm gonna give you some wrong answer. I have a
Okay, sounds good.
50% chance, I have a 50-50 chance of giving you the wrong answer real time.
No worries, Professor. All right, thank you very
Okay.
much.
Okay, thanks. Take care.